Okay, so thanks a lot for the invitation. So the talk will be in two parts. I'll start out by, since it's a pretty diverse audience, just some background on the KPZ equation and just what the status is of the exact computations. And then in the second part, I'll talk about some new results on the flat case. So especially in the first part, it's a kind of whirlwind tour of KPZ, so you should feel comfortable slowing me down and asking questions. So here's the KPZ equation. It's an equation for a height function. You can think of it as the height of one of these discrete models, which are graphed down there, evolving in time. So it's function htx. X is everything is in one dimension here. And it's evolving according to a heat equation. That should be the relaxation method. There's basically these three key terms in random growth that are being encapsulated here. One is the relaxation, which is just a heat equation. And then there's a forcing by space-time white noise, which is this term, C. And then the most important term here, by far, is this lateral growth term. So let me explain the lateral growth term. I've also chosen these halves and stuff. That's not important. You could choose any number there. Doesn't make any difference. So the key thing is that things aren't just growing up and down, but they're also growing in a lateral direction. So that if the growth here is lateral, then the vertical component of the growth is some nonlinear function of the derivative. Okay? And what that nonlinear function is shouldn't matter too much. It's probably a symmetric function in dxh. Even that wouldn't matter too much. So the idea of the physicist is that what you should do is you should expand this function. The first term can just be removed by a height shift. The second term can just be removed by spatial shifts. So the first thing you see which can't be removed is this quadratic term. So let's just drop the rest and put that upstairs. It's an incredibly naive idea, but it gives rise to this magic equation. So that's what's there upstairs. Of course, this is complete nonsense. I mean, look at these things. dxh is not small. So it's completely ridiculous. Okay. The equation actually existed in the literature before. It's also a model for fluids. It's the stochastic Burger's equation, which is just exactly what you get if you take the derivative, the slope. Okay. So that's just the Burger's equation, the viscous Burger's equation, plus the derivative of space-time white noise. And that's just completely equivalent to this equation. So you could think of fluids, you could think of height functions, and I'll show you some others. Okay. So what's it supposed to model? These random growth models are just these particular discrete growth models. I'll show you a couple now. Okay, so here's the simplest model. And this is a model you may want to think about a little bit. It's an incredibly simple model, and this one we can prove absolutely nothing about it. Okay, so it's the Eden model. So in the Eden model, you just start with a seed on a lattice, and then you add boxes. Well, there's 4 neighboring boxes. You just pick one at random and add it. And now there's, I don't know, 6 neighboring boxes, and you just pick one and add it. And that's the rule. You're just picking a box at random on the boundary and adding it. Okay. So the thing grows like that. And there. Okay. And then after a long time, you get this. Okay. Now, the large-scale structure is that the thing should grow. Okay, so t in some variable you call time times some shape. Okay, the shape may not actually be a circle here. It shouldn't be a circle here. Plus fluctuations, and the fluctuations are the size t to the chi. And the key thing is that in this 1 plus 1 dimensional situation, so this is 2-dimensional, but the boundary here is 1-dimensional. The boundary here is what's supposed to be KPZ like, right? So that's the 1 plus 1 dimensions. Is that you're always supposed to see chi equals 1/3, and the fluctuations are supposed to be universal. So you're supposed to see at the boundary, these fluctuations here are about t to the 1/3, where t is this radius. And the fluctuation process on this boundary is supposed to be a universal object. Okay?
Is t the radius or the number of steps?
The radius. That's why I said invariable, so that that's the radius. So it should be t times this shape. Okay?
So is there a constraint that the radius has to be a graph? Is it one?
No, this one isn't. It's not at all a graph.
Okay. So how is this related to diffusion limited aggregation?
It's not the same as diffusion limited aggregation. But if you had, suppose you took diffusion limited aggregation, but you had lots of particles instead of just sending in one particle at a time from infinity. So you had a density of stuff and it was doing diffusion limited aggregation, then it would look like this again. Okay. All right. But actually universal, the fluctuations are universal, but they should depend on the initial condition. So here we started in this curved geometry. And then what you're supposed to see are these fluctuations. Well, you're supposed to see this GUE distribution, t to the 1/3 times the GUE distribution, or an Airy-2 process if you're looking at this fluctuation on the boundary. On the other hand, if you started with flat, and I don't have a nice picture here, I'll have it in a second. So suppose you start at a half space and then let the thing evolve like that, then you're supposed to see the GOE distribution. So these things are supposed to be universal, but they do depend on the initial conditions. Okay, so here's another picture. So what Takeuchi and Sano managed to create is an actual physical Eden model in the lab made out of liquid crystals. So the liquid crystals sort of float around in this chaotic sea, and then they line up with each other and form this growing blob of the black stuff. So there, if you start with the seed, the thing grows like this. It looks very much like the Eden model. And then he can actually check to see that this is the GUE distribution asymptotically with the t to the 1/3. And here's the flat case. You just start the thing with a laser being fired through a prism so that it starts a line, and then the thing grows, and you get actually the GOE distribution. So this has actually been confirmed. Okay. So the type of models we're going to talk about are, well, there's this problem that there should actually be a height function. So let's make one with a height function. And the simplest height function is a height function which is just either a vertical line up or a vertical line down at every point. So this is the simplest possible height function. You can think of the height function as just a random walk path. All they do is they go up and they go down. Or you could code that with a particle. When it goes up, there's a particle. And when it goes down, there's no particle. So you can either think of it as particle configurations on a lattice with one particle or no particles at each site, or this random walk path. Okay? What the particles are going to do is that they're going to try to jump to the left with rate q and to the right with rate p, and let's assume that q plus p is 1. Okay? But q shouldn't be equal to p. And of course, when the particle jumps, the height thing will shift up. So there it goes. It jumps, goes up. So you could just as well think of it as these guys jump to these guys at rate p, and these guys jump to these guys at rate q. So you can either think of the random walk path. A symmetric random walk is invariant for this process. Okay? That's one of the reasons the process is very simple. It has a nice invariant measure, so it's very studyable. And corresponding to that, the two-sided Brownian motion should be invariant for KPZ. So this is supposed to be a microscopic version of KPZ. Here's a picture. This one. Okay, so here we're starting from flat. Flat means particle, no particle, particle, no particle, particle, no particle. Or just this little zigzag. And what you can see is that the thing's starting to look Brownian-like locally. Okay, but it still has this large-scale structure of a straight line. Everything's going up. So there's these growth up, which you have to subtract from everything. And one other thing you can kind of see is, can you see the lateral growth? It's maybe a little hard to see in the picture. Things sort of go like that. Okay. All right. So that's the model we're going to try to study. Okay. Now there's another class of models which is also in the universality class, which looks superficially very different. That's the directed polymers. Okay. So in directed random polymers, we'll have it a background of IID random variables on, say, z plus times z. Okay, so think of this direction as time and this direction as space. In the picture, the size of the random variable is just encoded by a color. Okay, so you have a bunch of ID random variables. And now you make an energy, the energy of a path. So here's a random walk path. Yeah. It doesn't matter. It's because all you're doing is weighting things by the sum of x's, so if the xi had some mean, it would just not change the model. So you might as well put 0. Okay. So assume xi has a couple of moments, not much else than that. Okay, so the energy of the path is just as you walk through, you collect all the x's as you go. Okay, and then you weight each path by e to the minus beta the energy. And then there's a normalization to make it into a probability measure. That's the partition function. Okay, so that's all the z is. There's two natural models. One is that we could fix the beginning point and the end point of a thing. So you would have random walk bridges from the beginning to the end point. And another is that you could fix the beginning point and just let the end point dangle free. Those are the two basic models. So the first one's called the point-to-point directed polymer, and the second one's called the point-to-line directed polymer. Okay. Now the connection to KPZ, well, what does this have to do with KPZ? Well, if you take the partition function, the partition function satisfies a discrete stochastic heat equation. Well, this thing's just basically z's just the sum of those, and that's just a discrete version of the Feynman-Katz formula. So of course it satisfies some discrete stochastic heat equation. This may not look exactly like a heat equation, but if you look at it carefully, it is. Okay. The KPZ type things are just logs of stochastic heat equations. So if you take the log of this equation, you'll get a long, complicated equation which will look like a discrete KPZ. Okay? And in fact, the way you should think of KPZ, let's go actually, is that KPZ, which is a very ill-posed equation, okay? KPZ is horrible because the paths of KPZ, so if you take the thing at time t and think of it as a function of x, it's supposed to be Brownian-like. In fact, it doesn't matter what you start with. Start with anything, that at any time later the thing will be locally a Brownian motion with the same variance, fixed variance 1. Okay, at any time later. And so this dxh squared is obviously completely ill-defined. It's just infinity everywhere. So the equation itself is extraordinarily ill-posed. But actually that doesn't really matter. It's just that the equation was just a really weird way to write log of the stochastic heat equation. So you take this stochastic heat equation, and one of the miracles of the subject is this equation is perfectly well posed as a normal Ito equation. And the solutions are strictly positive. And you take log of that, and that's called the Hopf-Kohl solution of KPZ, and that's the solution. So KPZ is just a kind of awkward way to write an equation for log of the stochastic heat equation. Now, if you did that,
of course, the stochastic heat equation has the renormalization built into it. You say Ito
that's
choices. So you're making a renormalization in this way, and you're just saying the other one required some renormalization.
There's a little bit of truth to that, but if you wanted to write, say, a Stratonovich version of the stochastic heat equation, you would find out that all it was the same thing, but with an enormous shift. So it actually doesn't matter. This is a very well-defined object. What you'll find is that if you take this object and you smooth out the noise, which of course, what does a stochastic PDE mean? Stochastic PDE means only this. It means you write down the equation with the noise smoothed out, remove the smoothing, and see if there's a well-defined limit which doesn't depend on how you did it. Okay? And here there is. There really is, except for these height shifts. Okay? But the height shifts are natural in this problem because you saw at the beginning the thing's going up. And now you're rescaling things into long time, so of course you have to pull things down in order to see these fluctuations. Okay? Okay, so this guy's completely well-defined, and log of it is the Hopf-Kohl solution of KPZ. Now, of course, if you did that, you would get, if you defined this and took log of that and tried to do an equation for it, you get into terrible trouble because the Ito term is infinity. But that also shouldn't bother you. Because if you smooth out the stochastic heat equation and now apply Ito, you'll get KPZ with just an enormous term, but the enormous term is completely well defined. It's completely under control. You know what it is depending on the modification. So again, this is just telling you how far you have to go up to pull down to see these fluctuations. Okay. And you know this is the true solution because it can be obtained as limits of microscopic models. And in this new theory of Martin Heyer, which I guess everybody has heard of, where he makes direct sense of KPZ, the solutions are, of course, these Hopf-Kohl solutions. That's the basic test of his theory, that he gets the true solution. Okay. Just to go back. So log of this Z is a KPZ-like object. And the one thing to think about with these directed random polymers is that your intuition might be that they, well, your intuition might be that either of two possibilities. As beta goes to infinity, this becomes this model of last passage percolation, right? As beta goes to infinity, you just see the path of the least energy, and that's called last passage percolation. So you might think either that the model should look like beta equals infinity, and the whole thing should be studyable in terms of the last passage percolation, or that for any small beta, this thing should look essentially like random walks. And both those intuitions are false. So what happens is that for any beta, the thing's highly localized around the path, but it's not the last passage path. Okay? There's a very complex battle here between the energy and the entropy of the system, and different betas, it balances on different paths. But it still finds a special path, which is its favorite path. Okay? And that's why...
But the fluctuation theory isn't.
But the fluctuation theory of the free energy is the same.
Yeah.
But that seems to be why it's difficult to prove. Okay. Okay. Okay, now I just want to recall the difference between the KPZ equation and the KPZ universality class. Okay. The first model I showed you, the Eden model, is a KPZ universality class object. But what you should not try to do is show that the boundaries in that model are approximated by the KPZ equation, because they're not. The KPZ equation is just another model of that type. And until t goes to infinity, you don't see that they're the same. Okay? So the KPZ is a model equation in that universality class. Okay. So there's two basic limits. If you want to see KPZ you can, from microscopic models, you can. But the microscopic model has to have a tunable nonlinearity in it. Okay? So you take the nonlinearity or the asymmetry, it's the same thing, in the model, and you tune that to be small while you do a diffusive rescaling. So you take your model, and every model has an analog of the height function. It's just the free energy or whatever it is in the particular model. Now you diffusively rescale that, but at the same time, you adjust your noise. Now if the noise was 0, so you adjust your nonlinearity, or you couldn't adjust the noise. But let's talk about the nonlinearity. If the nonlinearity was 0, if you had none of this lateral growth, then all you would have would be a Ornstein-Uhlenbeck process, and everything would be Gaussian. And that's called Edwards-Wilkinson class. So what you want to do is you want to get to KPZ by adjusting your nonlinearity to be small, keeping close to the Edwards-Wilkinson class, so that the thing gets to the KPZ equation. Okay? So you do that like this. You take your asymmetry or your noise, it's about the same thing, of size epsilon to minus 1/2 while you're doing this diffusive rescaling, and then the limit you get the KPZ equation. This is very, very different from the long time limits of models like the Eden model being governed by random matrix distribution, stuff like this, having this t to the 1/3 distribution. That comes because the true KPZ scaling is not this diffusive rescaling, but to take this epsilon minus 3/2, epsilon minus 1, epsilon 1/2 scaling. That says that the size of the fluctuations are 1/3 of the size of the time. There's the t to the 1/3. Okay? If you take the KPZ equation and rescale it like that, you'll get an equation like this. KPZ itself is not scale invariant. So you'll just get this. And it looks just like the diffusive term and the noise are just going to 0, and you're just going to get an integrated Burger's equation. Okay? So it looks like in the limit you just get the Burger's equation. But you don't. You get something highly non-trivial. There's some remnant of the noise that survives in the limit, which are these airy noises. So anyway, so in the true KPZ scaling, the fluctuations are of size 2 to the 1/3. And now you can see the spatial scale, because this is epsilon minus 1. The spatial scale is 2 to the 2/3. Okay. So just remember, the asymptotic fluctuations in the class are not governed by the KPZ equation. Your problem, if you want to show the Eden model has these fluctuations, not to prove it converges to KPZ, but to prove directly, go straight to this true KPZ scaling. Okay. On the other hand, if you take a model like ASEP, ASEP has this tunable nonlinearity in it. That's the Q and the P. So if you take Q minus P, if you take Q minus Q equals P, then you're exactly in the Edwards-Wilkinson class, and you're just going to have these Gaussian fluctuations. But if you take Q minus P small enough that you stay close to there, then you're actually going to converge to the KPZ equation in this diffusive scaling. So the way you get results about KPZ is to get exact results for some model with a tunable asymmetry, and then take the limit to get a result about KPZ. So that's how all the KPZ results are done. On the other hand, the first results in the field were exact computations under the true KPZ scaling for special models which have this determinantal structure. So you have exact determinants. Then you do this true KPZ scaling, and you see these random matrix distributions and the Airy processes. Okay. That was done by a lot of people earlier in the 2000s. Okay, so here's a picture of the whole thing. Okay, sorry, it's not very artistic. Just quickly. Okay. You've got these tons of models in this KPZ universality class. Some of them proved, and these are guessed, basically. And under this true KPZ scaling, they're all supposed to converge to this KPZ fixed point, about which we know very little, except that it's full of random matrix distributions and Airy processes and things like that. But what the thing is, we don't actually know what it is. It's a mystery. On the other hand, these models with no nonlinearity scale to this Edwards-Wilkinson fixed point, which is just this free equation. And it has this diffusive rescaling. Okay? We have a short list of models. Oh, sorry. So first of all, there's this short list of models here. The star means that they're solvable to some extent, for which one can actually prove part of these true KPZ limits. In other words, one has a determinantal structure, takes a limit of the determinants, and gets some sort of random matrix distribution out of it. Then we have a short list of non-determinantal models which have been discovered, which have these tunable asymmetries in them, or tunable noises. And we can tune those noises to stay close to this Edwards-Wilkinson fixed point and hit the KPZ equation, which is actually the line between the Edwards-Wilkinson class and the KPZ fixed point.
So, sorry, just to make sure, this
Yeah.
is not a line of fixed points. There's a flow along the line.
I'm thinking of the KPZ equation here with a parameter in it, which you can think of that parameter as in front of the nonlinearity, or the parameter is the rescaling. So if you do this rescaling, the KPZ will converge up to the fixed point. If you do this scaling with an epsilon large, you'll converge down to this Edwards-Wilkinson fixed point.
Well, I guess my question is really about the RG underlying the whole picture. Is there a relative collision in the sense that attached to the flows?
I'm just thinking of taking all the models and doing this simple renormalization. So take the height function and these.
Ask a specific question.
Yeah.
Why do you have two different lines coming from ASEP, one of them going to the fixed point, the
Right.
other going to the line?
Okay, so I take ASEP, and you're supposed to see that this line is red because it's this scaling. Okay, so if you take ASEP, and you rescale it like this, okay, then certain variables in it you can actually prove converge to GUE or something like that, which is this KPZ fixed point type scaling. The other thing I can do to ASEP is I can take ASEP and I can take this Q minus P to be small. So I steer the thing to not go straight there. Steer it down and go to the KPZ equation first. Then you get a limit in KPZ, and then you could go back up here to the KPZ fixed point. Does it make sense? Well, you're sort of rescaling space and time at the same time. This is the scaling in order to get this point, and this is the scaling in order to get this point. But at the same time, I have to tune the nonlinearity if I want to get there. Does it make sense?
This direct line you mentioned from ASEP to KPZ, that's you have tracing in it.
Well, in some cases. In some cases. So what's known, for example, is that if you take ASEP with this step initial data, then you'll get the Tracy-Whittem GUE distribution at the height function. That's proved by Tracy-Whittem. We'll see that in a second. Okay. There's also another sense in which KPZ is universal, which is that if you take KPZ-like equations, so here's a KPZ-like equation with a 4 instead of a 2. What happens if you take that guy? You could take this weakly asymmetric scaling. Actually, you get KPZ back. So the 4 just magically becomes a 2. We recently proved that with Martin Heyer. So the KPZ equation is sort of a special invariant equation.
Can you have deterministic equations that also belong to this family?
Yeah, well, that's a good question. So I don't think any are known, but I have a guess of one.
Where they get nonlinearity generates the noise.
Right. So my guess, it's a guess, it might be wrong, is that you take the Korteweg-de Vries equation. It also, if you start with white noise initial data, that stays. And I'm guessing that's in the same class. Okay. So yeah.
Can you say a few more words about the question mark? So what's known about this fixed point and what's the mystery about it?
Yeah, so what's known is that if you start with certain initial data, then you'll have certain Airy processes as the fixed time distributions of this thing. But everybody in this whole thing, well, most of them, are Markov processes. Okay? So as a Markov process, nobody knows what this thing is. We have a proposal of what it is, but it's not clear it's correct. Okay? So it's not known as the Markov. And this is something to remember. So every point in here is a Markov process. So the fluctuations are depending on the initial data. Okay? There are special initial data, though, because you're always doing this scaling. So you should sort of believe your initial data. There should be special initial data which are invariant under that should be the kind of initial data you expect to see interesting things. Okay? Any other questions about the picture? Okay. So now just to make it more precise, the KPZ universality class is actually supposed to divide into these sub-universality classes depending on the initial data. So this is the picture which you've get from these determinantal models by exact calculations. Okay. So the point-to-point initial data for the directed polymers, or you could, well, KPZ is a weird equation, so it has weird initial conditions. But if you think of the stochastic heat equation, it just means delta function. So start stochastic heat equation with a delta function. Then what you're supposed to see is that the KPZ height function should look like this constant times t, which we've always been seeing. And then this parabola. Well, the parabola is not hard to explain. It's just the log of the fundamental solution of the heat equation. But then on top of that is the important thing. There's this t to the 1/3 times the Airy 2 process in space. So that's what you were supposed to see at the boundary of this curved Eden model. Okay. In the point-to-line case, well, and this is from the movie. You'll see this constant times t, and then again t to the 1/3, but a new spatial process, the Airy 1 process, whose marginals are GOE, as opposed to these whose marginals are GUE. And then there's a bunch of other natural cases. You could start in equilibrium, which means a two-sided Brownian motion. What do you see at time t later? Well, you see a new two-sided Brownian motion, but that height shift is very non-trivially correlated to the Brownian motion. That's what you want to get your hands on. And then there's, okay, so those are the three basic cases with the right invariance. And then there's mixed cases, because you could start with one of these on one side and one of them on the other side. So that actually makes 6 basic processes. And one of the mysteries is that all these are given by determinants. Always in X, yeah. For fixed t in X, for fixed large t as functions in X. Oh, I see. Yeah, no, this is always on the whole line. Yeah. Actually, the periodic question is interesting, but it hasn't been studied. Yeah. Okay. So, yeah.
Is this conjecture that do but ensembles lead somewhere? Are there supposed to be some conditions for which you get statistics?
I don't think beta ensembles fit very cleanly in this picture, except a little bit of beta equals 2 here. The connection with random matrices, remember, is very tangential.
I mean, here, in these mixed cases, if you construct some strange the limit described.
Oh, what happens if you construct strange initial conditions?
Yeah,
Well, can you get a beta ensemble? Not that I know of.
Something else than 1 or 2.
Yeah, not that I know of. You might get a 4. You get 4s if you have some reflection symmetry of the noise. That's known now. Okay. Okay. So in other words, in the movie I showed you, that this process, the blue process, is supposed to be the area 1 process. Okay. So let's keep going. So now the big discovery of Tracy and Whittam in 2008 was that some non-determinental models also have exact solutions. So you have ASEP, the model I showed you at the beginning, and you're going to start with a wedge. So you start with a wedge, which is either the V, or you can think of all particles on one side. And then there's an exact solution for the height function at a later time. It's an exact solution. It's given by a very, very complicated formula, which involves determinants, but is not a determinant itself. It's not quite clear why the determinants are there, but the thing about this formula is it's conducive to asymptotic analysis. One thing to remember, the formula is only for exactly this initial data. The initial data is crucial here. You have formulas for precise, particular initial data. Okay. Anyway, if you do the asymptotic analysis, because you know that the height function of ASEP under this diffusive rescaling, as I showed you, with Q minus P tuned to be small to stay close to Edwards-Wilkinson, will go to KPZ. So you just do the asymptotic analysis, you get an exact formula for KPZ. Okay, so that's how the first formula for KPZ was done, and that's how all the formulas for KPZ are obtained. They're obtained by finding exact formulas in some microscopic model, and then doing this diffusive scaling in order to get the limit. Okay. And here's just a picture of those exact distributions as you scale from the Edwards-Wilkinson, which is this Gaussian, to the blue one, which is the Tracy-Whittam GUE distribution. I'm not going to show you the formula. The formula is essentially meaningless except that it exists. And it gives you this nice family of distributions crossing over between these two classes. Okay, but remember, this is just for the step initial data. Okay. Okay, so this started a race for the different initial data. So we have a race going on. This is for exact formulas for 1D distributions of KPZ at finite time. Okay, so the first ones were discovered by our group and Herbert's group in February 2010. And then physics proofs, and I'll go into the physics proofs in a few minutes, in March. Okay.
So the difference here is proofs, because I see.
Yeah. So physics means it's not rigorous, and I'll tell you how they're doing it. Okay, so it's kind of fun.
Rigorous and
It's kind of fun. It doesn't really happen that often. So the math proofs are before the physics proofs, right? Okay, so then half Brownian initial data. So half Brownian means that the stochastic heat equation is starting with 0 on one side and then e to a Brownian motion on the other side. And then again, you have an exact solution. So that was Ivan Corwin and I. And then a year later, Tomohiro came up with a non-rigorous proof. Okay, so, well, it looks weird, except now they start winning, right? So from there on, they start. Okay, so Brownian initial data means start the stochastic heat equation with e to a two-sided Brownian motion. Okay, so then the formula was discovered by Sasimoto and Imamura in 12, and it will be, a proof will come out soon. I don't know how soon. And then there's the ones I want to talk about, which is the half-flat and the flat formula. So half-flat means you start the stochastic heat equation with 0 on one side and 1 on the other side. And flat means you start the stochastic heat equation with 1 on both sides. Okay. So formulas were discovered by Calabrese and Ledussal. Calabrese and Ledussal, and some formulas by Dutsenko also. And I'll show you the rigorous version of them. Okay. What? Oh, great.
Now, this is supposed to be exact formula, I thought.
Yeah.
What does it mean for an exact formula not to be rigorous?
Yeah. It's a good question. I have no idea what happened to the rest of the PDF, so hopefully.
I mean, these are Replica computations.
Yeah, I'm going to show you the computation. I'm going to show you how they do the computation. Sorry, we're going to get it back, and hopefully it's there. Before I do that, yeah, okay. So let me just tell you about the status of one-point fluctuation results for non-determinental models. So now this is KP. So the first thing I showed you was KPZ equation scaling results. Exact formulas for KPZ equation. But then there's analogous long time limits in KPZ universality class for these non-determinental models. So just the status of these is that there's just a number of models that one can do. ASEP, the KPZ, or the continuum random polymer. This new model QT-ASEP, which was discovered by, I guess, Tomohiro and Wataria, and then Borden and Corwin. And O'Connell-Yor polymers, another exactly solvable model, and then there's this log gamma polymer. So we have this short list of 5, maybe plus 2 or 3 others, models for which one has exact enough formulas that one can get these one-point distributions asymptotically. Remember, one-point distributions. And now look at the initial data. So what's known in ASEP, point-to-point, or half Brownian, as we just saw. Point-to-point, half Brownian, point-to-point, half Brownian, point-to-point. So the main thing is that all these results are really about the point-to-point case. That's really all that's been done. Now, remember, the two cases which are sort of most important for polymers are point-to-point and point-to-line. So the big one that's missing is this point-to-line. The point-to-point case is much more understandable than the point-to-line. So the GUE is sort of understood because you have some polymers. Actually, Alexei showed one in his talk. And then there's the O'Connell-Yor polymer, for which you sort of can get GUE from the model exactly, as beta goes to infinity or some parameter. And then you have this umbrella of McDonald processes, which also explains this GUE in the point-to-point case. But the GOE this is a big mystery. Why you're getting GUE in these growth models is really strange. The GOE arrives in the growth models because it's the suprema of the Area 2 process minus the parabola, as Kurt Johansson discovered. But there's no Area 1 process in random matrix theory. And the fact that this thing has the same distribution as a top eigenvalue of a GOE matrix seems to be just a coincidence at this point. There's no explanation. Okay, now here's the answer to your question. Here's what the physicists are doing. Okay. Okay, what they're doing is you take the stochastic heat equation, and there's a special fact about it. Okay, so if you take the solution of the stochastic heat equation, now at fixed time but a bunch of spatial points, okay, and take the expectation of this product. So if you like, they're the correlation functions. Then, okay, you call this function ut x1 through xn. It satisfies exactly a heat equation. This is a rigorous fact. It's easy to check. It satisfies dTu equals Lu, where Lu is this attractive delta Bose gas, which is just the Laplacian plus this delta interaction between the particles. Now notice an attractive delta Bose gas. When it's a minus sign, it's the standard delta Bose gas. So this is kind of a weird one. Okay. Now the thing about this model is that you know the eigenfunctions and eigenvalues. You know them exactly. They're complete. You know absolutely everything about them. They're extraordinarily complicated, but you know what they are. So in principle, you can reconstruct U as a series if you're given your initial data, just from the eigenvalues and eigenfunctions. That's not hard. The problem is that you want to reconstruct the distribution of Z from U. And that's false. Because you can check easily that the moments grow basically e to the n cubed. And you're not even close. It's just completely false. And all you're doing is testing far out things in the tail of this distribution. Okay? In fact, you can see this number here coming easily, because if you take the Tracy-Whittem distributions and you take their moments, you get this e to the 1 over 24 n cubed. And that's what you're doing. You're just looking way, way out in the distribution. Okay. Okay, but that doesn't stop them. So what you do is you write down a generating function. The generating function is given by this. This series, of course, is divergent like you can't even imagine. And then you regularize it using the following Airy trick. So the Airy trick is just that you know if you have an Airy function and you take its Laplace transform, then you get e to the n cubed. So what they're basically doing is they're summing this series, minus 1 to the n e to the n cubed, using the following idea. You just write this thing using the Airy trick, change the order of the summation integration, and this sum inside is easy to perform, and so you get that. And so that's the answer. So that's what this sum is. And that gives you the right answer. Or you could take this thing and you could do what's called Mellon-Barnesing it, which is just to write an integral of sine to give you the poles, and you get the same answer. Okay. So what they're doing is this is working through these strange divergent integrals, sums. But the important thing is that the calculations you do using the replicas seem to have some very, very interesting algebraic structure, and seem perhaps even to give more solvability than the determinantal models. So you seem to be able to get a lot out of this, even though you're working through this non-regress thing.
The KPZ Universality class is the one where the Airy trick function
Where the Airy trick
works.
gives you the right answer. That's a nice definition. Okay. All right.
So where are the I mean, this doesn't look like replicas.
Well, these are called replicas here.
And they never take the limit n going to 0, and they
Well,
multiply to...
This is sort of a sophisticated
So it's
version
not
of n.
what I would have thought of.
Well,
It's similar.
It's not so dissimilar, I understand.
Well, this is a very sophisticated version of limit of z to the n of minus is log. That's all. How they described it to me is slightly less nonsense than that. Okay, so now we can talk about the new results. Okay. Okay, so I'll just tell you the result. The result's about ASEP. So you take ASEP and you take flat ASEP. So flat ASEP means the particles initially 0, 1, 0, 1, 0, 1, 0, 1. P over Q is called tau. And H is that height function I told you about. And now you take a certain exponential. This is a tau deformed exponential. Transform of the height function. Takes its expectation at time t. And it's given by a Pfaffian. Okay. So it's a Fredholm Pfaffian.
Where's x sub tau?
That's coming. It'll take a minute to explain.
Okay, good.
For now, think it's just some Q deformation of the x function. Okay. It's what it wanted. That's all I can say. It's given by a Pfaffian of a kernel, which I'll show you in a second. The Fredholm Pfaffian is just a name for this Fredholm series of Pfaffians. Or you could think of it as the square root of the Fredholm determinant if you don't worry about the plus or minus sign. And the Pfaffian is just the, if you don't know what this is, you can also just think about it as the square root of the determinants. Maybe it's the easiest. So let's answer what's the x function. Okay, so here's some qx function. So if you take x and you take q versions of it, there's a bunch of choices you can make. And the standard choice is to take the thing called the little e exp. And that's given by this Pockhammer symbols, or perhaps easier to say is just this series, where this is the q factorial. And the q factorial is just the product of the q numbers, and the q numbers are just those. Okay? And here I call everything q, and unfortunately there's a bit of a problem in this business because q was told to be the name of the jumping rate to the right. So q is tau in all the formulas. Okay. Okay, and then there's another one called big E, which is also given by a Pockhammer symbol, or you can think of it like that. These are the standard q exponentials, but then there's a third one which wasn't known about so well, which is this exp. So exp is sort of in between. Instead of this thing over 2, it's over 4. Now, why is that interesting? Well, it's actually the sum of x to the k over the symmetric q numbers. The symmetric q numbers is just writing the q numbers. They're sort of like these ones, except you do it in a symmetric way, so it has this q to 1 over q symmetry. Okay? So the exp is the special quantum deformation of the exponential function, which has this q to q inverse symmetry. And actually it had to. So let's go back. Because there's a special symmetry of flat ASEP, which is that if you change q and p, so that's tau to tau inverse, then they're just walking the other way, so the thing's going down. So h just becomes minus h statistically. So this formula had to have this tau to tau inverse symmetry. Okay.
In the formula, you wanted the fraction of n to 0t, or?
Yeah. No, the t is hiding inside the k. You could probably write it that way, but this is the way we wrote it. Okay. It looks very pretty, except now I'm going to show you what's k. Wow, okay. So the thing is, k had to be a little bit complicated. Because, sorry? That it had to be complicated? Yeah. Sort of is, because if you take the Pfaffian version of GOE, even that's not very simple, right? This is a formula which, it's not the standard formula, but it's equivalent to the standard formulas. But you see, in this formula, so if you take Pfaffian of this, you get GOE. That's true by some computation. But the thing is, these functions in here, if you think about it, they're actually very complicated functions. They just happen to have names. Ours just don't have names. So there are all these strange Q hypergeometric versions of the area function sitting inside this thing. I tried to make it simple, but okay. This is just some strange Q hypergeometric Bessel function. Oh, okay. So that's what it is. Anyway. Okay. So anyway, so this gives an exact formula for the generating function of the difference here. One thing I should say, because you're probably wondering, this generating function does actually determine the distribution of H. It's not obvious, but it does. Okay.
It's clear that the fluctuations look much more ups and downs.
Yeah, that's just because these Tracy-Whittem distributions aren't they're actually not centered. It's not just that they're not symmetric; they're not centered. Okay, so actually there were earlier formulas of Young Lee for flat and half-flat ASEP. I'll show you them to you in a second. They don't seem to be useful for asymptotics. And there's earlier KPZ formulas. Yeah.
Well, I could hold it till the end, but since you have all these connections with Q functions and Q exponentials and so on, is there an underlying algebraic structure involving either, I don't know, Kac-Moody or quantum groups or so that explains what...
I'm the one who tried to make you suggest that, right? I said, from quantum groups. This is actually the Q exponential they use in quantum groups. And this is the big question, actually. I'd like to ask anybody in the audience whether there's a nice algebraic structure.
ASEP is known to have UQSL to C.
Sorry?
UQSL to very simple quantum group C. And that should be right.
And that should be somehow the reason for these formulas. When I show you the proof, it's completely not clear in the proofs why these things are happening. That's the key question. Okay. There were earlier KPZ formulas of Calabrese-Zhang Equation I told you about. Those formulas are non-rigorous, and I should say they're non-rigorous not just because of the replicas. They're way more non-rigorous than that. They're basically done using replicas plus Mathematica.
There's no such thing. You know, I have to quote Ed Nelson. To say something's very non-rigorous versus non-rigorous is like saying she's not pregnant, but there's no such thing. If it's not rigorous, it's not rigorous.
I don't agree. Some things you just have to fill in epsilons and deltas. Anyway, okay.
If that's rigorous, that just means someone has written down the fine points. That's a little different.
Okay, so anyway, I got to keep going or I won't have time. I want to show you where we get the formula. You do get the GOE Tracy-Whittem distribution, the t goes to infinity limit, and we get a sensible version of the Calabrese-Zhang flat KPZ formula in the weakly asymmetric limit. Okay, here's how we get the formula. So first of all, this is Yuheng Li's formula for flat ASEP, or half-flat ASEP. So it's an exact formula for the, well, this is the number of particles to the left of x at time t, which is basically the same as the height function. It's an exact formula for this, but it's as a sum. And you see the sum's this k bigger than m. And the biggest problem with formulas like this is this exponent isn't in any form for asymptotic analysis. So no one's been able to do anything with this formula, though it's existed in the literature for a couple of years, and many people have tried. So here's how we get a formula. So we start with this Borden-Korowin-Sasimoto ASEP duality. So what the ASEP duality tells you is if you want to get this function, utx, which is this, now this you should think of as a microscopic version of the product of z's in the replica. Okay? So you take, instead of z, you take basically e to log tau times the height function and take its multiple at a bunch of times and take this expectation. So this thing satisfies this discrete version of the delta Bose gas. So here's the forward equation, and then you have some boundary conditions which correspond to these deltas. Okay? And then it has to satisfy the correct initial condition. If it satisfies these three conditions, there's only a unique solution, so it is that thing. Okay, so that's what we learned from Borden-Korowin-Sasimoto. The problem with this scheme is that if you're given an initial condition, you don't know how to find UTX. And it's only been done in cases where you sort of knew UTX already from McDonald processes, which is basically this point-to-point case. So how do we find UTX? We just guess. And the way you guess is you actually stare at Yuheng Li's formula and try to see what makes Yuheng Li's formula work. And then you just sort of throw those things into the existing formulas of Borden and Corwin from McDonald. And you find out that this is the extra term you should add. So without this term, this is basically the formulas of Borden and Corwin coming from McDonald. But then you add this extra term and you find out that it works. And this gives you the half-flat initial data. All of this stuff, I didn't say it and I should have. All of this is for half data. So this is data which are 0 to the left of some point. Okay, that's very important. So we can only do half-flat this way. Okay, so you get a formula for the half-flat moments this way. Okay? And you can check it works. And then you go through a sequence to try to make a generating function, and you produce the following generating function. So there's the generating function of half-flat ASEP. So half-flat ASEP, remember, means that you have zeros on one side and then particle, no particle, particle, no particle to the right of the origin. Okay. Then you get this generating function, but notice this capital E here. This turns out to be rather important. So the generating function is complicated, and it's full of these Q-hypergeometric functions. It's convergent, but only just. I have to use this capital E. If I use any of the other exponentials, it's actually divergent. It's really tight.